Electrical engineering is a field that encompasses the study and application of electricity, electronics, and electromagnetism. It deals with the generation, transmission, distribution, and utilization of electrical energy, as well as the design and development of electronic devices and systems. Key concepts in electrical engineering include voltage, amperage, resistance, and power. Voltage, measured in volts, is the electrical potential difference between 2 points in a circuit. It is the driving force that causes electric charge to flow. Amperage, measured in amps, is the rate of flow of electric charge through a conductor. It represents the amount of current flowing in a circuit. Resistance, measured in ohms, is the opposition to the flow of electric current in a circuit. It determines how much current will flow for a given voltage. Power, measured in watts, is the rate at which electrical energy is transferred or consumed in a circuit. It is calculated as the product of voltage and amperage. The relationship between voltage, amperage, and resistance is described by Ohm's law, which states that voltage equals amperage times resistance. This fundamental law is used to analyze and design electrical circuits. Electrical circuits are composed of various components, such as resistors, capacitors, inductors, and transistors connected by wires or conductors. Resistors limit the flow of current in a circuit. Capacitors store electrical energy in an electric field. Inductors store electrical energy in a magnetic field. Transistors are semiconductor devices that can be used to amplify or switch electronic signals. Electrical engineers design and analyze circuits to perform specific functions, such as amplifying signals, filtering noise, and controlling motors. They use a variety of tools and techniques, including circuit simulation software and measurement instruments, to verify the performance of their designs. Electrical power systems are used to generate, transmit, and distribute electrical energy to homes, businesses, and industries. Power plants generate electricity using various sources, such as fossil fuels, nuclear energy, and renewable energy. Transmission lines carry electricity over long distances from power plants to substations. Substations step down the voltage of electricity for distribution to local areas. Distribution lines deliver electricity to individual customers. Electrical engineers design and maintain power systems to ensure a reliable and efficient supply of electricity. They also work to integrate renewable energy sources into the power grid and develop new technologies for energy storage and transmission. Electronics is a branch of electrical engineering that deals with the design and development of electronic devices and systems. Electronic devices include diodes, transistors, integrated circuits, and microprocessors. These devices are used in a wide range of applications such as computers, smartphones, televisions, and medical equipment. Electrical engineers design and develop electronic circuits and systems to perform specific functions, such as processing data, controlling machines, and communicating information. They use a variety of tools and techniques, including computer-aided design software and microfabrication processes, to create electronic devices and systems. Electrical safety is a critical aspect of electrical engineering. Electrical engineers must design and install electrical systems that are safe for people and property. They must also follow safety codes and regulations to prevent electrical hazards such as electric shock, fires, and explosions. Grounding is an important safety measure that provides a low-resistance path for fault currents to flow back to the source, preventing electric shock. Circuit breakers and fuses are used to protect electrical circuits from overcurrents, which can cause fires. Electrical engineers also work to develop new technologies for electrical safety, such as arc fault circuit interrupters, which can detect and interrupt dangerous electrical arcs. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It provides detailed requirements for wiring methods, overcurrent protection, grounding, and other aspects of electrical safety. Electrical engineers must be familiar with the NEC and other applicable codes and regulations to ensure that their designs comply with safety standards. Here are some more detailed examples of electrical engineering principles and their applications. Firstly, consider the calculation of voltage drop in a circuit. Voltage drop is the decrease in voltage along a conductor due to the resistance of the conductor. It is important to calculate voltage drop to ensure that the voltage at the end of a circuit is within acceptable limits. The voltage drop can be calculated using Ohm's law, where voltage drop equals amperage times resistance. For example, if a 120 volts circuit has a current of 10 amps and a conductor resistance of 0.1 ohms, the voltage drop would be 1 amp times 0.1 ohms, which equals 1 volt. Secondly, there is the selection of appropriate wire size for a circuit. The wire size must be large enough to carry the current without overheating. The NEC provides tables that specify the allowable ampacity of different wire sizes. Ampacity is the maximum current that a conductor can carry continuously without exceeding its temperature rating. For example, NEC table 310.15. B16 specifies that a 14 American wire gauge copper conductor with a temperature rating of 75 degrees Celsius has an ampacity of 20 amps. Thirdly, the grounding of electrical equipment is crucial for safety. Grounding provides a low resistance path for fault currents to flow back to the source, preventing electric shock. Electrical equipment is typically grounded by connecting it to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode must be properly sized and installed to ensure that it can effectively carry fault current. Fourthly, the overcurrent protection of electrical circuits is essential to prevent fires. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. Circuit breakers are resettable devices that trip when an overcurrent occurs. Fuses are non-resettable devices that melt and open the circuit when an overcurrent occurs. The size of the overcurrent protection device must be appropriate for the ampacity of the circuit conductors. Fifthly, the calculation of power in a circuit is important for determining the energy consumption of electrical devices. Power is calculated as the product of voltage and amperage. For example, a 120 volts appliance that draws 5 amps consumes 600 watts of power, which is calculated as 120 volts times 5 amps. Sixthly, power factor correction is used to improve the efficiency of electrical systems. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the current is not being used to perform useful work. Power factor correction involves adding capacitors to the circuit to compensate for the inductive reactance of electrical loads. This improves the power factor and reduces the amount of current required to deliver the same amount of power. Seventhly, the design of electrical lighting systems involves selecting appropriate light sources and fixtures to provide adequate illumination for a given space. Light sources are characterized by their luminous flux, which is the amount of light emitted per unit time, and their color temperature, which is a measure of the color of the light. Lighting fixtures are designed to distribute light in a specific pattern and to protect the light source. Electrical engineers use lighting design software to simulate the illumination levels in a space and to optimize the lighting system design. Eighthly, motor control circuits are used to control the speed and direction of electric motors. Motor control circuits typically include a motor starter, which is used to start and stop the motor, and a speed controller, which is used to adjust the motor speed. Motor control circuits can also include protective devices, such as overload relays to protect the motor from damage. Ninthly, the design of electronic filters involves selecting appropriate components to filter out unwanted frequencies from an electronic signal. Filters can be designed to pass low frequencies, high frequencies, or a specific band of frequencies. Filters are used in a wide range of applications such as audio processing, image processing, and communication systems. Tenthly, the design of communication systems involves selecting appropriate modulation techniques and transmission media to transmit information from one location to another. Modulation techniques are used to encode information onto a carrier signal. Transmission media include wires, cables, and radio waves. Electrical engineers design communication systems to meet specific requirements for bandwidth, data rate, and reliability. In summary, electrical engineering encompasses a wide range of concepts and applications related to electricity, electronics, and electromagnetism. Electrical engineers play a critical role in designing, developing, and maintaining the electrical systems that power our world. They use their knowledge of electrical engineering principles and their skills in problem solving and innovation to create new technologies and improve existing systems. The field of electrical engineering is constantly evolving, with new technologies and challenges emerging all the time. Electrical engineers must stay up to date on the latest advances in the field to remain competitive and to contribute to the advancement of technology. This involves continuous learning, professional development, and participation in industry events and organizations. By embracing these opportunities, electrical engineers can continue to make a significant impact on society and to shape the future of technology.